An overhanging beam is a structural element that were used commonly in engineering and construction, characterized by its extension, whether it supports at one or both ends. This will allow the beam to support loads over a greater span without the need of other addition supports, making it has more advantage in various architectural and civil engineering applications. This design helps to balance the loads of the beam while reducing bending moments and shear force in the central section of the beam. Overhanging beams have many advantages, including extended spans without any additional supports, architectural flexibility for cantilevered structures, and also more efficient load distributions. This type of beam is commonly used in bridges, buildings for balconies and canopies, and also in industrial structures such as platforms. The structural analysis of overhanging beams was used to determine the reactions at the supports, shear forces, bending moment, and also deflections by using methods such as numerical methods and software tools. For example, a simple 10 meters overhanging beam that has 2 meters of supports at each end and extend to 2 meters of the supports on each side will reduce bending moments in the middle section that lead to a more efficient structural design. Overall, overhanging beams offer significant advantages in terms of span length, load distribution, and structural design, making them a versatile and good choice in construction projects. So for the objective, how can we ensure that an overhanging beam, subjected to various loading conditions, can structurally meets all the safety and performance requirements? First, determine support reaction. By doing the calculation of reactions, we can accurately calculate the vertical reactions at the supports due to the applied uniformly distributed load, central point load, and additional point loads at the overhangs. This step is crucial for understanding how the beam transfers the applied load to supports. Next, load distribution analysis. We can analyze how the loads are distributed among the beam and how the overhanging sections affect the support reactions. This helps in identifying any potential imbalance in the load distribution that might cause instability in the structure. The second one is analyze structural behavior. By doing the deflection calculation, we calculate the deflections at various points along the beam using appropriate methods such as the double integration method or numerical analysis. Ensure that the deflections are within permissible limits to prevent structural damage or failure. Next, we use the stress analysis. Assess the internal stresses within the beam caused by the applied load, particularly focusing on the bending stress. Ensure these stresses do not exceed the material yield strength to avoid plastic deformation or failure. And the last is ensure structural integrity and safety. We verify the maximum bending stress by compare the calculated maximum bending stress with the allowable stress for the beam material. This ensures that the beam can safely withstand the applied loads without exceeding its capacity. Next, we make the recommendation for design modification, which is if the analysis indicates that the beam does not meet performance criteria, suggest design modifications such as changing the beam's dimension, material, or adding additional supports. This recommendation aims to enhance the beam's structural integrity and ensure it meets safety and performance standard for construction.
Okay, Assalamualaikum warahmatullahi wabarakatuh. So today I will explain about the finite element analysis using McWay steps. First of all, we need to open the McWay and insert all the coordinates of the nodes. Then we select the new element and click on line 2. Connect all the nodes to create an element in a straight line as the assignment assigned us to design an overhanging beam. Then we insert all the nodes and all the support and the forces. Then we click on the geometric section and choose the I section and insert all the required data. As for the geometric section, we choose isotropic section and fill the data. Right click on the first node on the left and choose constraint, and then click on the fixed support. While the node that on the right hand side, we will click for pin support. We will select the node that will assign for the forces and insert all the data. So the result is shown as the first node will assign for pin support, and then the forces, and the next node is fixed support, and the last one on the overhanging side, there will be forces. And lastly, we will click solve to run for the solution.
Now we will move to the results. As you can see, there are materials properties and also geometric properties used in the data, which following the article's beam specification. And for me, I just want to highlight the positions of the node and the force applied in the data. As you can see, there is the node number 3, which is at the middle, the node number 1 and also the number 2 is at the left and also the right. There are also two forces applied as P1 and P2, which is the yellow arrow. The results also shows that there are two dimensions, which is two dimensions and also 3 dimensions bigger after insert in McRae. The members use different types of loop to compare with the article's result. So you can see there are 4 tables which indicates the different types of load, which is 1 kilonewton, 2 kilonewton, 3 kilonewton and also 4 kilonewton. To get to the work's objective or the purpose of this task, the results must be obtained is for the displacement, shear force and also moment after the load is applied to the overhanging beam. So I will explain when the load is at 1000 Newton or 1 kilonewton. The data for node 1 and node 2 retrieving none or 0 displacement, the node 3 got about 30.548 mm displacement in y direction. That means the node 3 implies a significant deflection after the load is applied. For reaction force, node 1 is 0.497 kN and the node 2 is higher at 1.497 kN where the beam is experiencing major shear stress. For the node 2 is where the beam is overhang, so that's the reasons why the shear stress is increased at that node. That is the moment. Node 2 and node 3 have a very small reaction moments, but it still indicate that the beam tendency to rotate under the applied load. The pictures given, you can see that there are different colors of the beam, where the blue colors indicates the lower value and also for the black color of the beam, which means that that is where the critical points and also the maximum value is located. So from here I want to conclude that the node number 3 retrieving the highest value in terms of shear, moment and also displacement, and the location where the risk of failure is located because they have to handle their own load and also the overhanging load.
Assalamualaikum. I will be discussing about the structural analysis of a beam subjected to various load, focusing on deflection, shear forces and the bending moment observed in our experiment compared to theoretical values. Notably, node 3 is identified as the critical node due to its maximum displacement and shear forces. Experimental value of deflection were significantly higher than those reported in theoretical articles. This discrepancy highlights the importance of empirical validation in structural analysis. Regarding shear force, maximum shear again happened at node 3. The experimental shear forces closely match theoretical value, with both experimental and article value are the same. Despite this consistency, assumption was made due to the small strain value suggests a need for careful consideration of the shear data. The highest bending moment was observed at node 2 with a critical value at 3000 Newton load. No significant bending moment were recorded on the x-axis and y-axis, indicating that the critical moment will happen along z-axis only. So these are the data that we got by plotting referring to our experimental and theoretical value. You can see a significant difference between experimental and theoretical value, but it necessitates accurate experimental validation. Variation can arise from measurement procedure, beam dimension, load application method, and also boundary condition. These discrepancies highlight potential human error and difference in data interpretation and processing. Our experiment revealed the critical impact of load on beam deflection, shear force, and bending moment. Empirical data often deviate from theoretical model, underscoring the need for rigorous experimental validation. Understanding this difference is vital for a reliable structural design and safety.
Okay, Assalamualaikum. For the conclusion, of course, our objective, which is to analyze an overhanging beam by using finite element analysis or FEA through McRae software. So, for our conclusion, we successfully met our objective by determining an important parameter including displacement, rotation, and all the reaction forces. Okay, next what we can conclude from our mini project is what is the difference between using finite element analysis and manual method. Okay, by using finite element analysis (FEA) instead of manual method, it is allowed for more accurate and detailed analysis of complex structures. FEA also handles intricate shapes and varied load condition, which can provide precise stress and strain distribution across the entire structure. Also, by using FEA, it saves time by performing rapid calculation, enable easy design optimization, and offer visualization that help understand the behavior of the structure under different conditions. But manual methods are limited in handling complex problems and can be time-consuming and less precise.